Hello, this is Jose Luis here at Parametric Camp, and welcome to a new hands-on video in this series, Advanced Development in Grasshopper. In this video, we're going to continue developing this prototype of the Parametric Camp Grasshopper plugin, or whatever we're calling this. And we're going to continue with the work that we've done in previous exercises. But for this one in particular, we're going to focus on creating a collection of components that are going to perform operations on meshes. However, I would like to keep in mind that the purpose of this exercise is not to learn mesh manipulation, algorithms for mesh reduction, remeshing, none of that. The goal of this exercise is to illustrate the previous video in this series where I was talking about how to use external libraries, how to bring them into your code, and how to use code that someone else has provided for you. So what I would like to do in this exercise is use a very popular and super powerful library called, where is this? That is called Geometry 3 Sharp, that comes with a lot of really powerful mesh reduction and mesh remeshing operations. So what I would like to teach you in this video is how to download that library, how to compile it into, how to download the source code, compile it into a library, bring it into your custom C# script components, and create your own components that perform mesh manipulations. So for example, examples of that is this head, that is the mesh that I'm working with, has a particular topology of meshes and vertices. But what I can do, for example, is I can perform an operation of reducing the amount of vertices to create a low poly version of this head. So that's one thing we're going to try. And another thing that we're going to try is called remeshing. Remeshing is the operation by which we redistribute the triangles, the vertices, etc., so that they become more homogeneous along the mesh. So you can see that I'm going to set, for example, a target length for the edges of this face, and the more passes I do in refining this mesh, the closer I get to a target where all the triangles have roughly a edge length of whatever number I have set here. That implicitly comes with a sort of smoothing of the mesh. You can see that I'm losing resolution here on my nose. I'm losing resolution on my ears. They have kind of disappeared, right? But it's implicit in the process, all right? What's interesting is that we're going to learn a lot about using this library called G3 that comes with these objects called dmesh3 that contain all these powerful ways of remeshing and reducing themselves. Again, not about the actual algorithms. I'm not going to get into that. So with that, I think we are ready to start. However, if you actually want to learn about meshes and how meshes are defined with vertices and faces, I have a different video. I have a video on my introduction to parametric modeling where I touch specifically mesh topology, and how to create them from scratch. So if you're interested in that, you probably want to check out the other video first before going into this one. Probably a link will be popping up somewhere on a card, or the link will also be in the description of this video. All right. Beautiful. So with that, how about we go and we start taking a look first at where to find that library, how to compile it, how to bring it into Grasshopper, and how to build components using the power that that library is giving us. Let's take a look at how that works. Let's begin. So as I mentioned in the introduction, we're not going to write our own mesh simplification, remeshing algorithms, whatever. That's actually quite tricky, and it requires like quite some expertise. So what we're going to do is we're going to rely on the kindness of other people that have made this work for us and have created libraries of code that they have put out there for free as open source, and that we can benefit from. This is fortunately very often the case these days with a lot of people who contribute open source code to the world, and that researchers, academics, or even for commercial purposes sometimes that you can use. So in this case, for the case of mesh manipulation, I am actually very fond of this library called Geometry 3 Sharp, created by Gradient Space, which I believe is kind of a brand name that the author, Ryan Smith, has been working on for quite some time. Ryan's work is amazing. You should definitely check it out. He was the author of Mesh Mixer, which ended up acquired by Autodesk, and he also works for Epic Games, making a lot of 3D modern. He's a really, really interesting guy. So in his website, Gradient Space, you have a set of libraries that are available for use. It has like a Grasshopper, a slicer library, G-code library. He's very much into 3D printing. And he also has a set of tutorials for using C Sharp, his work in Unity or standalone. So for example, a lot of the code we're going to be writing is informed by these tutorials that he has here. So if we go to open source and if we go to the Geometry 3 Sharp, you can see that he has a link to a GitHub repository which contains the code for the Geometry 3 Sharp library. This library is basically a full geometry kernel. It has vectors, it has a lot of curves, operations, etc., polylines, blah, blah, blah. But especially, it's really good for mesh simplification and mesh algorithms. So if you're interested in learning more, you can just go to the README and look at the documentation. There's a bunch of tutorials. There's lists to the core methods that you can find. It takes a while to get used to someone else's code, but if the author is nice enough to provide a good documentation, then that's typically a good way to start. So we have the C Sharp library, the open source is here, but what do we do with this? If you're perhaps like a bit new to C Sharp development, you might feel a little lost. So typically in C Sharp, we use two things in order to use someone else's code. If you go to releases, you can see that here in tags, you can see that there's a bunch of official releases, so packages that the author has bundled and that the author considers working fine. Maybe it has some bugs, but it's something that should be published as usable. But if you look closely, in this case, what we get is that these releases are Nuget Packages. Nuget Packages is the form that Visual Studio has to have some kind of central repository of libraries that people can add to their own projects. This would be very interesting if we were already working with a Visual Studio project, so we just insert the NuGet and we're good to go, or if we were working in Unity, which I believe has Nugget support as well. I'm not entirely sure about that right now. But because what we need is for our Grasshopper plugin, what we need is just the DLL, the file that contains all the code. What we're actually going to do is, instead of going through the NuGet package, what we're going to do is we're going to download the source code. We're going to open it in Visual Studio and we're going to compile it ourselves, which is something way simpler in C Sharp. It's much simpler than it actually sounds. So what I'm going to do is, I'm not even going to bother with forking, blah, blah, blah version. I'm just going to download the whole repository as a zip file, and I'm going to put it on my desktop, okay? If I look through my 17 windows, you can see that the zip file is now here. I am going to extract it into geometry, blah, 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 master, and now I have this folder. And in the folder, you can see that I have the Visual Studio project that contains the full library. So if I do, for example, if I click here on Geometry 3 Sharp, blah, 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 you will see how all of a sudden I have a solution with the Geometry 3 Sharp project loaded all. And then if I go to core, for example, and I can see, for example, I have vector array, I have a classes for vectors arrays, I have a utility class, I have units, I have, for example, G3 interfaces, file system, I have a lot of stuff. I can have dvector, I can actually check the source code of the project, which is extremely, extremely cool. So I'm actually really happy. Thank you very much, Ryan, for your contribution. But because we're not going to modify the source code, which we could if we wanted to extend it, write our own functions. If we found a bug, we could do it here. We're not going to need to do that. What I need is to take this project and to compile all this code into a DLL that then I can load into Grasshopper. So the way I'm going to do that is by going to here to build solution, and then there's going to be some stuff going on here, and it told me that, yeah, this work, it succeeded, so we're good. And then inside of the project, this folder has popped up called bin, and in bin and in debug, you can see that I have these two files. This is a debug file. We don't really need that. And I have the geometry3.dll file that contains all the code. All right. So that's going to be the file that I need. So what I'm going to do now is I'm going to take that file and I'm going to paste it into the file that next to this folder where I have the files that I'm going to be using in Rhino. So if you see, I already have all my previous exercises and all of that. We have it here. So this is like the prototype for our plugin, correct? And then here I have a mesh components section where I'm going to be writing new components that are loading from this library. And then here on my Rhino viewport, I have this low poly version of a 3D scan of my head that I did a few years ago. Do I look? Oh. I have this 3D scan of my head, which is a mesh object, which I'm going to be using for debugging and testing. Okay. All right. So we are ready. We have Rhino file, Grasshopper file, and we have the compiled file, which is next to our Grasshopper file. So the next step is going to be writing our first component that takes a regular Grasshopper mesh and converts it into a G3 mesh. So let's take a look at how that works. The first thing we need to understand is that for the same reasons that I have explained, or even more obvious reasons than what I have explained in my previous video, it turns out that because in Rhino we are working with meshes that have a particular internal structure, a particular way they work, those meshes are not going to be compatible with the way the G3 library treats its own meshes. And it turns out that the G3 library has its own mesh structure called the dmesh3. And if we actually look at the documentation, you can see that it's a dynamic indexed triangle mesh, and it has all this like goodness about why it's great and what elements are linked to each other and the way the internal storage is. It's actually a really interesting read if you are interested in learning more about how different meshes can be, about how meshes, excuse me, can be represented in different ways. And we can actually even look at the code. So if we go to the source code, you can see that inside of mesh, there is the mesh3 class. And you can see that it's actually quite a code base of almost 2,000 lines of code, more than 2,000 lines of code on how to represent meshes. So it's actually, this is the goodness, this is all the power that we're drawing from bringing this library into Rhino, into our Grasshopper plugin, and all the power that we're gaining. The problem is that because Rhino meshes are different than G3 meshes, there's going to be a process of conversion that we're going to have to do ourselves. So let's first create a component that is going to take any Rhino mesh or Grasshopper mesh and is going to convert it into a dmesh3, the ones that are used, the one that is used by G3, because we will need that to plug those meshes into any other component that we write that makes mesh operations. So how are we going to do that? So I'm going to open the mesh components. I'm going to drop here an empty mesh parameter. I'm going to set this mesh here, okay? And then I'm going to write a C# script component that is going to take any mesh, sorry for shouting, and it's going to take any mesh and it's going to spit out a dmesh3, okay? So then I'm going to plug this in here. I'm going to make sure that this mesh is actually a mesh. So, oh, you can see it. I'm clicking on mesh. So the input is a fully qualified Grasshopper mesh. And then I'm going to write my code here. First of all, the first thing I need to do is I need to remember to load my assembly. So I'm going to load my I'm going to load my geometry 3 library here. I'm going to load that assembly. Okay. And then the next thing that I'm going to do is that I need to load that assembly into my code. I need to do that by namespace. So if I didn't know what the namespace was, I can look at the source code and I can see that the namespace is G3. So that's what I'm going to do. I'm going to say using G3. All right. And then for conversion, what we need to do is we need to take this mesh and we need to convert it into a dmesh3 object. So I have dmesh3, right? Dmesh3 object. So what I could say is I could create a dmesh3 variable. I'm going to call it dmesh, and that could be a direct cast from the mesh that is coming in into the dmesh object. I might feel inclined to do that. This is what we did in the previous video as an example. But if I do this, I'm going to get an error, which is that the computer doesn't really know how to convert from a Rhino.geometry mesh, so that is the type of the object that is coming from the input, and the G3.dmesh3, which is the target mesh that we're going to be using in G3. It turns out that because it's not a type that is derived from one another, they're just so different from each other that the computer doesn't really know how to cast one from the other. So that's a little bit of a problem, but fortunately, because meshes are meshes, what we will be able to do in this case is that we will be able to actually do that conversion ourselves. The conversion is going to be just as simple as creating a empty dmesh3 object and then taking all the vertices from the original mesh and copying it to the dmesh, and then taking all the faces of the original mesh and copying them to the target mesh. We're going to have to write a little bit of an algorithm to make that operation, but it's going to be actually very, very easy. So let me show you how to do that. So I'm going to say, this is my algorithm, all right? And the first thing that I would like to do is I would like to create an empty dmesh. The way to do that is creating an empty dmesh3, and then I open parentheses, and you can see that I get a bunch of options. Do you want normals? Do you want colors, UVs, tree groups? I want everything. So I'm going to say true, true, and true. Also, by the way, when you're working with a new library, you don't really need to know all of this. How would you know? The way to know about all of this is that you have to read the documentation, you have to check some tutorials in order to understand how the author, what kind of methods, what kind of patterns they give you to work with. And I know that I have to do true, true, true because I actually spent a full live stream researching for this video and trying things out, running into problems. And I would like to very, very strongly credit Victor Lin, who is part of the community, who was on that live stream. He was helping me real time and then took the file and gave it a second check, whatever. And it was super helpful to make this happen. So thanks to you, Victor, who might be watching this video right now. So all of the things that I'm going to be showing, I don't know them off the top of my head. I know them because I've done some research, I've looked through the documentation, and I've tried things out. Okay, so don't freak out if you take a new library and all of a sudden you don't know how to use it. That's actually the norm, not the exception. So I'm going to create an empty dmesh3. All right. And then once I have the empty dmesh3, what I would like to do is I'm going to copy all the vertices from the original mesh to the dmesh one. So copy all vertices. So what I'm going to do is I'm going to write a for loop, and I'm going to say for I equals 0, I is less than the amount of vertices in the original mesh. So mesh.vertices.count, right? And then I++. What I'm going to do is I'm going to go over each one of those vertices. I'm going to copy it, and I'm going to add it to my dmesh. All right. How does that look like? I'm going to create a point3f object called vertex, and that's going to be the vertex that I'm going to take from the list. So from the mesh, from the original mesh, from the vertices list, I'm going to take one at a time. And then what I'm going to do is that to my dmesh, so dm, which is empty right now, I'm going to append. You can see that I have two options, append triangle and append vertex. You probably know that we're going to be using append triangles as well very soon, right? I'm going to append a vertex, and you can see that it asks me for a vector 3D, but that's not going to be a Rhino vector 3D. It's going to be it's going to be, damn it. It's going to be a G3 vector 3D, or is asking me for coordinates. So what I can do is v.x, v.y, and v.z. Okay. The only thing to keep in mind here is that I'm using 0.3f, just because vertices are 0.3s, but also because append vertex takes floats and not doubles. It's just something to keep in mind. Let's see if this works so far. Something is not working. No overload. Append vertex takes in 3 arguments. Interesting. That's not how it works. Oh, wait. Oh, that's true. I actually did change the code when I was researching this. Hold on. Let me take a quick look at this. Hold on. Okay, sorry for the introduction, for the interruption. So it turns out that I had forgotten when I was doing this research, I did actually extend the original library to accept 3 doubles as an input for append vertex. Because otherwise, if you do dm.append vertex, the 4 overloads that we have is either a vector 3D, which is not a Rhino vector 3D, it's a G3 vector 3D, or 2 new vertex infos, or like a mesh and the ID, whatever. And it just feels convenient to have these three inputs, right? The alternative would be, if we were to not extend the library, what we would need to do is to say vector 3D v3 is equals to a new vector 3D, and then all these parameters here. However, this is not going to work well. Actually, it does work well. It doesn't work well because there is an ambiguous reference. Exactly. So vector 3D now that I have included G3, it turns out that both Rhino and G3 have a class that is called vector 3D. So now the name vector 3D is ambiguous. The computer doesn't know if this is Rhino or if it's G3. So we could solve this here by saying G3 and then G3.vector, blah, 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 and then use this, and now this works fine. But I kind of like the possibility of having 3 doubles as an input. So why not just do a small modification? Since it's open source, we can extend the library and then just add more methods to ourselves. So I think that's an interesting exercise, so we're going to do it. So I'm going to undo all of this, and I would like to the original library to add a new method, append vertex, that takes 3 doubles, just because it's convenient for us. So let's do that. So what I'm going to do is I'm going to go to the original. This is my original Visual Studio project, the source code that I downloaded. I'm going to go to the D3 mesh class, and I'm going to try to find the append vertex method, which is right here. And if I press F12, you can see that I go to where this method is defined. Turns out that we saw before that there's 4 overloads. So there's append vertex, another append vertex here, and there's probably more on top, append vertex here, and append. You see, this is the vector 3D from G3. Okay, so how about we extend the library here, and we say, I'm going to extend the library with a new overload to accept 3 doubles. So that's going to be public integer append vertex, and this is returning an integer just because all the other overloads are. So I want to stick to the convention. So double x, double y, and double z. I do that, and then what I can do now is here I can create a vector 3D v. It's going to be equal to a new vector 3D with the x and y and the z properties. All right. And then what I'm going to do is I'm going to use this vector to pass it on to this append vertex here. So what I'm going to do is I'm going to say integer result is going to be equal to append vertex with this vector that I just created. And then I'm going to return that result because this append vertex gives me an integer back, which is probably either the ID of the vertex or some integer flagging whether if the operation went fine or not. And actually, what I can do is I can shorthand this a little and then just say, can you just return whatever you are getting out from append vertex? Okay. So by doing this, I have just extended the library. I created a new method that simply gives me a new interface of 3 numbers to an operation that is basically saving me some code to write some code on Grasshopper by embedding this code inside of the library. So now it's just going to be as simple as building the solution. The solution gets compiled. I get a new DLL file, and that new DLL file should be somewhere here. So this is my desktop, bin, debug, geometry 3D from this timestamp. So that looks good. And then what I'm going to do is I'm going to put this back. I'm going to overwrite this one. I'm going to delete this one, which I cannot because it's probably being used by Grasshopper. So I'm going to save this. I'm going to shut everything down, shut Rhino down. I'm going to try to delete now, and now it's good. I couldn't delete it before because it was being used by Rhino. So I'm going to place here the new version. All right. And I'm going to start things again. So I'm going to open Rhino. Oopsies. Nope. No. Sorry, I opened the wrong Rhino. No. Okay. So I'm going to open mesh components and I'm going to open my new file and I can see that, oh, and now it's working. Now it's working because it's picking up the new DLL and this append vertex actually works now. And if I do dm.append vertex, you can see that I have now 5 overloads. The first one is XYZ, then the vector, then the two vertex info, and the mesh, and the blah, blah, blah. So nice. That was a way to learn how to extend the library. That was actually pretty cool, I think. I'm going to give myself a pat in the back. All right. So we had the library we had the component. Sorry. Let me recap. So we had the mesh that was empty. We have copied all the vertices from the original one to the target one. Okay. So now what I would like to do is I would like to do something similar where I'm going to copy all the faces. All the faces. And I actually forget if I also extended the library for this, so we may have to do it again. I don't know. For int I equals 0, I'm going to iterate over all the faces. Faces.count, faces.triangle count. We're going to do triangle count because we're only going to copy the vertices that are the faces that are triangles, because dmesh doesn't take quad faces, but Rhino accepts faces that have 4 vertices. So we're only going to copy the triangle ones. And then I++. And then what we're going to do here is we're going to say, first, let me take the mesh face that is going to be at mesh.faces give me the face that is at position I. All right. And then if that face, actually, I think this code doesn't. So let me try with all of them. I get the face, and then if mf.is triangle, then what we do is we say dm.append triangle, and then this one actually has indices, so I don't need to, and then I can do mf.a, mf.b, and mf.z. Remember that triangles are typically defined by the IDs of the vertices that the triangle is joining. So if the triangle is joining vertices 3, 5, and 7, so that is the order in which you need to plug them. So that's typically integers. All right. Beautiful. And then with this, I think we should be good. Outputs. So that's going to be dmesh3 is going to be equal to this object that we just created, dm. Is that true? I'm going to run this code. It looks like it works. And I got an object of the type g3.dmesh3, which I think it's looking okay to me. All right. Now, one thing that I'm going to do is, because this idea of converting from a, I'm not going to do that. I'm just gonna keep it here, or not. I'm going to do it. Sorry, we're learning tutorials. So, because this idea of converting from one object to the other might be something that I might do a lot over the course of this plugin development, why not just abstract all of this into a function? So why not create a function here? I'm going to create a public function that returns a dmesh3 object, and that is going to be called convert mesh. And it's going to take as an input a regular Rhino mesh. Okay. And then what I'm going to do is I'm going to copy all of this here. So inside of the function, given any mesh, I'm going to take that mesh and I'm going to create a new empty mesh, copy all the vertices, copy all the vertices, and then return that object. If that is the case, then what's nice about this is that I can delete all of this, and then the main algorithm is just as simple as converting the original mesh into a D3 mesh. All right, the code is a little cleaner, it's more elegant, and then I can also now copy this function and copy it to a different component and then reuse my code. Things are nicer, more encapsulated, etc., etc. All right, beautiful. What are we going to do next? I think the next thing that we're going to do now is we're going to do a little bit of deconstruction, and then we're going to write a component that takes a dmesh3 and prints out some properties. So the amount of faces, the amount of triangles, etc. Just some information. Okay, let's take a look at that. I've gone ahead and created this C# script component that is taking in a dmesh3, and that is going to output a bunch of properties that we can learn from dmesh3 objects. This is going to be super interesting. So the first thing we're going to do is I need to type this input. So remember, I need to right click here and say that the type has to be of some kind, but we have the problem we discussed in the previous video. We don't have dmesh3 here because it's not part of the Rhino common or the Grasshopper framework. So we're going to have to rely on conversions. So I'm going to choose here the system object just because it's the root of that all objects inherit from. And then I'm going to double click here and start doing some. So first of all, I'm going to write my algorithm here. And the first thing that I would like to do is I would like to take this generic object and cast it into a dmesh3 object. So how are we going to do this? Well, because it's coming from a dmesh3, we already know that this data is correct. So the only thing that we need to do is we just need to cast it so that it's properly typed here in our algorithm. The way we're going to do this is by saying dmesh3 dm is going to be whatever is coming in from the component, which I'm going to cast to an object of the type dmesh3. However, this is not going to change to work because I have forgotten to reference the assembly and all the things that I should have done. So I'm going to right click here, manage assemblies. I'm going to drop here my geometry3 library that I have it here under recent, so I don't even need to look for it on my system. And I need to remember to say here using G3. All right. And as soon as I do that, then this works. And then this algorithm, this is already picking it up. All right. So what is next? Well, the next thing that I would like to do is I would like to do some queries here. So what I would like to do is I would like to say, well, first of all, the output is valid is probably something that I can read from that mesh in itself. So I'm going to make this a little bigger. So if I have my D mesh and I type dot, you should be able to see. I don't know why we're not seeing this, but you should be able to see like a list of all the different properties that I can read from the object. All right. So if you check the documentation, it turns out that there's this function called check validity, which given it takes a false and it takes a fail mode, return only. And if this works, yes. So I'm not sure, I'm not free. I'm not sure why the autocomplete is not working. Oh, that's probably because when I loaded the IDE, because I loaded the reference, but I didn't refresh this. So let me try this again. dm dot exactly. The autocomplete was not working because I loaded the assembly and I loaded this, but when this script editor opened, it didn't load the assembly, so I didn't have it in memory. So I can now say, you can see that I can do check validity, and then I can allow non-manifold vertices, so I don't want to allow that, and I want the fail mode, if it's not valid, to tell me that it's not valid. I don't want to throw an error. I don't want to use any debug assistant. So that's what I'm going to do. And if I do that, you can see that now it is valid. All right. Another thing that I probably want to check out is vertex count. There has to be something dm dot vertex count. Is there something like that? Vertex, yes, vertex count. So I can see how many vertices there are, right? I can say triangle count, dm dot triangle count. Let me run this. I'm going to run this, and you can see 500. And we can also add here edge count, no? Edge count. What if we do that? So I'm going to say this, 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 and this. And I'm going to load this again. And here under edge count, dm dot edge count. All right. And this tells me that this mesh has 1500 edges, which is kind of cool. All right. Now, what about edge length, the average, etc., etc.? Well, it turns out that DM, the meshes, they have this thing called the edge. No, sorry, I'm running too fast. Turns out that the G3 library has a method that can give me statistics about a particular mesh. And it does so because those statistics are not... So the way this works is that I can say mesh queries. This is a class that lives inside of G3. Mesh queries dot edge length stats. This is a function that takes in a particular mesh, so that's going to be dm, and it returns as outputs, it returns computation statistics about the different lengths of the edges. Why is this like this? Why not just dm dot minimum edge, maximum edge, etc.? Well, that's probably because the designer of this library thought that perhaps performing those computations was expensive, and that it would only be worth if the user actually needs to know them. But embedding them by default in a mesh was probably too much of an overhead. So they probably thought, well, people who want to know the length, the average length of the edges, is probably going to be like not a very popular thing. So why waste resources and memory on that? So if people want to know that, they should just ask for that information right away. So explicitly. So you can see that in order to get that information, we have out parameters. So I'm going to have to define a priori minimum length, average length, and maximum length. And then here I'm going to say out minimum length, out average length. I think the order is not correct. It's maximum length and then out average length. Okay. And with that, I might be able to say minimum edge length. I'm very sloppy with the typing today. Minimum length, and then let's see if this works. Yes, the minimum length for my mesh is 0.06 units, whatever that is. So I'm going to copy paste this and say average length, and then maximum length, and then that's going to be average length, and then maximum length. I do this, I press this, and you can see that I have some additional stats related to my mesh. Okay, beautiful. What's to remember about this? I had to load my assembly so that both components had access to the same dmesh3 structure, and I had to remember to cast this structure, to cast this object, this generic object, to a dmesh3 so that I could access its properties. All right, beautiful. So now I have a way of constructing dmesh3s and have a way of retrieving information for them. So I think it's right, we're right there. It's the right time to now start using all the powerful goodies in the library to start doing things such as remeshing, vertex reduction, and all the cool stuff, all the cool mesh manipulation stuff. Let's take a look at that. As I mentioned before, one of the most powerful things about this library is that it has a lot of functions and a lot of methods to perform topological changes to meshes. That means changing the shape, changing the amount of vertices, triangles with different optimizations, reductions, targets, remeshing. Is actually quite interesting and very powerful. If you want to learn more about what's possible, you can go to the tutorials. And for example, we're going to do an example right now that is derived from mesh simplification. So just simply removing vertices in a strategic way. And we will also do a few more examples about remeshing, for example. So what we're going to do now is we're going to write a component that takes a mesh, a dmesh, and then given an amount of target vertices, it tries to reduce that mesh to that many vertices. So for example, we can see that the head that I have here has 502 vertices. And if we wanted to reduce it and make it more low poly, for example, to 100, we could use this component that I'm about to write right now. So, so how does this work? All right, so the way we're going to do that is by, I have created this C# script component that is taking a dmesh. It takes an amount of target vertices and an integer, and it's going to spit out this mesh, the dmesh, and it's going to also tell me the amount of vertices that it had before and the amount of vertices that it ends up after the simplification, okay, just to verify. The way we're going to do that is I'm going to open my editor here, and then I'm going to start with my algorithm as I typically do. So what I'm going to do is I'm going to say algorithm, and then I'm going to say, what I'm going to do is, first of all, I have the dmesh that is coming in, okay? What I would like to do is, first of all, I need to cast that dmesh to an object, because as we said before, this is a generic object. I need to cast it to a dmesh structure. Now, the second thing that I'm going to do is I'm going to clone the dmesh. All right, I'm going to clone it because since I'm going to modify it, what I may not want to do is to modify the original dmesh that is coming in from the Grasshopper component. It turns out that Grasshopper typically doesn't do this. It doesn't modify things that are coming from the inputs, because Grasshopper has a way of creating clones and making sure that you're not referencing original objects, but it only does that with Rhino and with Grasshopper types. If you have your own custom types, it doesn't do that. So that's why what I need to do is I need to make a clone of this to make sure that the modifications and the remeshings are happening on the clone and not on the original mesh that is coming from before the input. So the way to do that is I'm going to create another variable, dmesh3. I'm going to call it, actually, I'm going to call this one the cast, and I'm going to call this one dm. And that's going to be a new dmesh3 object. And if you start looking down, you can see that actually there is an overload for the constructor that takes a copy and allows you to create an empty one as a copy of a different one. So I'm going to use this. I'm going to say here cast, and then true. I want all of this. Yes, I want all of this. And now I have a new object that is a copy of the previous one that I had. That's pretty cool. Okay. Now, again, how do I know this? I know this because I've done some homework, I did some research, I went through the documentation, and I found that there was this method, and I also went through some trial and error, and I found out that if you make changes on the original copy, then you will make changes to the previous object, which led to some. So you don't need to do this. You don't need to know this out of the box, and any new library that you start working with, you will need to get familiar with how that library works, the documentation, etc., to make sure that you're using it correctly. Okay, so there's always like a little bit of a learning curve when it comes to working with new code that someone else is giving you. All right. Now, what I could do now is before I do anything, what I can do is I can make sure that I output how many vertices this mesh has just before I make any changes to it. So in my previous vertex count output, I'm going to output dm.vertex count. So whatever it is right now, I'm going to output it. And if I run this code, this should give me 502 like it did before. All right, cool. So what I'm going to do now is I'm going to reduce the mesh. The way this is done in G3 is that you create an object called a reducer, and I'm going to call this R, and I'm going to be equal to a new reducer object that needs a D3 mesh as an input. Okay? And then once I have created this reducer object loaded with the mesh, then to this reducer object, I can ask many things, many ways of doing reductions. And if you're curious, you can see fast collapse, blah, 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 reduce to edge length, to triangle count, etc., etc. And what I'm going to use for this one is to reduce this to a particular target vertex count. So that's going to be whatever is coming in from target vertices from the input. Again, how do I know this? Because I went through tutorials and I found out that this is how it works. All right. Beautiful. And then the outputs are going to be the mesh out. It's going to be this object that I have reduced, dm, and final vertex count is going to be dm.vertex count. All right. And if I do this and I run this code, you can see that I get the dmesh out, I get the previous vertex, and I get the final vertex count, which is now 100. All right. So can we check this out? I'm going to hide the original mesh, and I'm going to make sure that in the preview, I can preview the mesh edges so that I can see those triangles. I'm going to hide this one. I'm going to hide this one, and I'm going to, I'm not getting a pre-visualization. That is weird. Let me make sure. I'm going to plug in here a mesh, and I'm going to plug it into the dmesh out. Oh, but I get an error. What is going on here? Well, it turns out that Grasshopper cannot visualize the mesh that we have reduced. Why? It cannot for the same reasons that we had here. It turns out that dmesh is such a different structure that Grasshopper has no default methods or no default knowledge of how to take something that is given from a third party and turn it into a mesh that is renderable by Rhino. That's why we cannot really see it here in the viewport right now. So what is the solution to that? We need to do the opposite process that we did here. Just like we had a mesh to dmesh converter, we're going to have to write a component that does dmesh3 to Rhino mesh converter. Okay? Just as simple as that. And then if once we have that conversion working, we will be able to plug in here a dmesh3 to Rhino mesh component and be able to visualize that. Okay. All right. Shall we get to that? I think that's actually going to be quite easy. So let's write a dmesh to mesh converter. I have now created this C# script component that takes in a dmesh in, and I'm going to make sure that this is on the type system object, and it's going to spit out a regular mesh. And I already have a mesh component here and a panel just ready for whenever this works. And for the time being, I'm going to plug this into directly to the original conversion to make sure that if we get the original head converted back to a mesh, then that probably means that the conversion happened correctly. So how about we now write some code to go from a dmesh3 into a regular mesh. So as we typically do, I'm going to cast the object dm is going to be equal to dmesh3 from dmesh3, and I forgot to add the library, so I'm going to have to do using 3, and I'm going to add here the assembly, which I forgot to do, and this now works. And now here, what I would like to do is the opposite process. So I'm going to create a new mesh, and I'm going to create a new empty Rhino mesh. I'm going to copy all the vertices, I'm going to copy all the faces, and then I'm going to spit that out through the component. All right. So I'm going to create a new mesh. Copy an empty Rhino mesh. So that's going to be a new mesh like this. All right. I'm going to copy all the vertices. So that's going to be for int I equals 0, I is less than dm dot vertex count I plus plus. And then what I probably want to do is I probably want to say if dm dot is vertex. So this is a check that we were doing because we were getting some problems with some vertices that were not correctly copied. So this is just a check to make sure that the vertex is valid. All right. It's a G3, it's a dmesh thing. So what I'm going to do is I'm going to copy the vector. So dm dot get vertex. I'm going to get the vertex at position, get vertex at position I, and you can see how the return type is a vector 3D, but remember it's a G3 vector 3D, not a Rhino common one. All right, and then what I need to do now is to the original mesh M to vertices, I want to add a vertex at coordinates x, y, z. So that's going to be v dot x, v dot y, and for the and v dot z. And you can see that for the G3 vector 3D class is not uppercase, but it's lowercase. All right. All right. So I have copied all the vertices. Now I can just copy all the faces. So same thing for I, int I equals 0, I is less than dm, triangle count, I plus plus, and then this is going to be equal. And then if dm is triangle, just checking in, and actually this is probably parentheses. If dm, if this is a triangle, then what I'm going to do is I'm going to retrieve the index of the triangle. So I'm going to say dm dot get triangle at position I, but you can see that the return type is this weird thing called index 3i. Index 3i is basically a collection of 3 integers. You imagine a vector that instead of doubles had integers. It's the same thing. It's a G3 structure that contains 3 integers that represent the IDs of the 3 vertices. So, and again, all of these things I know because I was reading the documentation. So I'm going to create a variable of the type index3i, which I'm going to call t for triangle. And then what I'm going to do is to the mesh, to the faces, I'm going to add a face that is going to have 3 indices. And the indices are going to be t dot a, t dot b, and t dot c. All right. All right. And just some sanity. When we create meshes from scratch, all the normals are not there. The normals are not calculated dynamically. And that's not good because if then we visualize the mesh, we're not going to get like nice shading. The shading depends on the normals. So what's interesting to do is to make sure whenever we create meshes from scratch in Rhino, to make sure that after we've done everything, we rebuild all the normals so that they get nicely rendered in Rhino. So now the outputs, we're ready. So mesh, the output is going to be this object M that we just created. And ta-da! Things are looking good. So you can see that for this one, I am getting a visualization. Actually, I don't even need this because this is the main output. So I'm getting a visualization of a Rhino mesh that has been converted from the D3 mesh that I had here. All right, so this is great. So we're ready then to now take this and see what the effect of the reducing the vertices, what the effect was. So now I'm going to just plug this in here. And what we're going to see is that something happened and it's not working. Something is not working here. And this was actually kind of one of the big problems that we faced when we were doing research for this video. And again, Victor Lin actually helped me a lot to figure this out. For some reason, we are not entirely sure why. For some reason, it turns out that when you make a reduction to the mesh with the G3 library, there is something about the structure of the vertices and the faces that happens internally that keeps that mesh valid within G3, but it doesn't. It becomes an invalid mesh for Rhino terms. We're not sure what's going on, but what we found through doing some research is that if we actually took the reduced mesh and we created a new clone of that mesh, then all the invalidity and all the misreferences and whatever was going on actually went away. So what we did here was, and I'm going to copy this paste here. For some reason, the reduced mesh had invalid vertices after the reduction. And this gets solved by recreating that mesh and making a copy of that reduced mesh. Again, we don't really know why this is going on, but we found that this was a solution. If Ryan Smith is watching this and he wants to chip in, I will be super happy to hear what's going on. And then what I'm going to output is, instead of this, is copy. All right, we're not going to output the reduced mesh, but that copy that we made from the reduced mesh. Beautiful. All right, so then, well, that's true. Then it turns out that now I am perfectly reducing that mesh, and that mesh gets converted into a native Rhino mesh that I can now see reduced. And check this out. So now more vertices all the way to the top, and now less vertices all the way to even just like a super, super low poly 17 vertices kind of head. All right. How cool is this? Huh? All right. Again, this is very cool. Again, thanks to Ryan Schmidt's work from Gradient Space, which made all of this possible. All right. Beautiful. So we have a component that reduces a mesh to a particular target amount of vertices. Turns out that the G3 library gives us method to reduce meshes also for target faces and for other measures. Do you want to take a look at how that works? Let's implement more of this. So to this example, I have added two more components that I did offline, and because they're so similar to the triangle one, I'm just going to show them how it works. One of them is a mesh reduce triangle. So this one is the same as the vertices, but instead of target vertices, what we get is how many triangles do we want to end up with. And remember, this mesh right now has 1,000 triangles. But if I reduce the count of triangles, you can see how all of a sudden I start getting a very similar effect. I get a low polygon version of the face, right? All the way down to 4 triangles or even 3 triangles and 0 triangles. So the minimum is basically these 4 triangles. This is the most oversimplified version of my head, really, which is kind of cool. And you can see that the code is the exact same thing. So we're casting, we are avoiding, we're cloning the object so that we avoid changes to the original one. We reduce it, but instead of using vertices, we use triangles. And then we clone the object again to avoid invalid vertices. All right. And that's the one that I'm plugging in here. And there's a similar one that is called mesh reduce edges. And the idea is that you can create a very similar reduction where what you do set is the minimum edge length. So what you're basically saying is I'm going to keep all the triangles whose edge is longer than a particular value. So I'm going to plug this in here in the visualizer. And then you can see that right now, because I have 0, I am not really cutting out any vertex. But as I start growing, you can see that all the edges that are short start disappearing. And then my head only remains with very large triangles. All right. So that could be also an interesting operation if you are interested in that. Okay. So these are 3 different ways of reducing the mesh. Now, when I say reducing, I mean reduction, because what these 3 components are doing, so the algorithms that are fueling these 3 components, what is happening really underneath is that the actual topology, well, topology might not be the right word, but the mesh in itself, when it gets reduced, the only thing that these components are doing when reducing the mesh is removing elements from the mesh. So it's either removing vertices or removing faces or removing edges. But anything that remains after the reduction is actually not changed from the original. So when you reduce vertices, what you do is you keep original vertices, but you're not moving those vertices around to reshape the mesh. So for example, you're not really redistributing the meshes so that the triangles are more homogeneous or something like that. It's more just a simple culling, if you will, which is good because it's a very fast operation. But if we actually wanted to be to make more drastic changes in the meshes, so for example, redistribute the vertices so that they look more homogeneous. So you can see that in this mesh, some triangles are really big here and some triangles are very small here. So maybe we want to come up with ways of remeshing things in a way that makes the distribution of triangles more homogeneous. So G3, the library, gives us also ways of doing that. So the last component that we're going to write is going to be a remesher, and that is going to accept some targets, and then it's going to basically change the whole topology of the mesh to adapt to those targets. Let me show you what that's going to look like. So in order to not make this video ridiculously long, I've also copy-pasted some code that I did offline while doing my research. And I created this component that is called Mesh Remesher. As usual, it's also using the Geometry 3 library. It takes in a dmesh input, right? And then what it takes us also as an input in order to work is basically a target edge length. And then how many passes do we want to do in terms of refinement? What this component will try to do is it will try to take your original mesh and it will try to redistribute. And I'm not even sure if it creates more or less vertices. I'm actually not sure about that. But what we will try to do is redistribute all those vertices so that the length of the edges of the faces is as homogeneous as possible. The result of this is that we will have a mesh that will look like all the triangles are almost the same size, more or less. But it's actually a really, really nice practice, especially if you're going to be using these things for like 3D printing, etc., etc. The target length is how big those lengths are going to try to be for the edges. And if we're setting the edge length, now that I don't think about it, it's probably going to need to add more vertices for sure. So that's, and the amount of passes is how many iterations of this calculation of this remeshing the component is going to do, because it turns out that it cannot calculate this thing just in one operation. So the more passes you do, the more the solution converges to this target edge length that we are setting here. So how does that code look like? Very, very similar to everything that we've done before. We cast the object from a general object, we copy it to avoid making changes to the mesh that is coming from the previous component, and then we remesh it. And here is where the difference is. Before, we were using a reducer class that was loaded with the mesh. In this case, we're using a remesher class that is also loaded with the mesh. What happens internally? Why they're different? I'm gonna let you check the open source code. But long story short, there are a few parameters that you can tweak, so you can choose whether if you want to prevent flipping in the normals, and whether if the target is an edge length, the amount of vertices, whatever that is. Here, I'm going to be setting the edge length as the target. And then with a simple for loop, what I'm going to do is I'm going to run a remeshing pass as many times as the input here. So it's just a simple loop that is calling basic remesh a bunch of times. And after that, just like we had before, I am cloning, I'm copying that mesh again because we were having the problems of the invalid vertices. Okay, and it gets output. So let me show you how this looks. So if I get passes 0, you can see that the mesh doesn't really change. But if I start cranking this up, one mesh, 1 2 3 4 5 6 7 8 9 10, you can see how the triangles in my head start becoming very homogeneous, even though also my face is kind of, let me bake this to make sure. Can we bake this? Yes, I'm going to bake this. This is my remeshed head, and this is my original head, which I'm going to copy somewhere here. All right. Can you see the difference between the both of them? My original one has triangles all over the place, and this one has triangles that are fairly homogeneous, more or less. I'm losing resolution on my nose, I'm losing resolution on my ears, but so it implicitly it has like a kind of a smoothing effect that could also be interesting depending on what you are trying to do. All right, but the more passes, the better. And then to make sure that this target length is correct, something that I can do is I can analyze my mesh with the component that I created before. And you can see that the minimum edge length in this case is 0.1. The average is 0.14, which is pretty close to the target that we set. So that's great. And the maximum is 34. So the range is pretty small too. And you can see that the amount of vertices and triangles and edges has increased from the original one, which is also kind of interesting. So this is giving us an algorithm that is changing drastically the topology of that mesh. All right, beautiful. And I think with that, this is probably enough for this video. The whole purpose of this video was to illustrate the idea of taking an assembly, taking a repository, taking a bunch of code that has been provided to us as an assembly from open source or from maybe a library that we license and we pay for it for commercial use, whatever that's coming from, but being able to import that library and use it to our advantage in some other platform. You can see that because it's C#, it's very easy to bring in and to use. We just need to be wary that, for example, in the case of meshes, we needed to do translations between Rhino meshes and D3 meshes in both ways, right? And we also needed to be wary that there are certain ways the third party works. So we need to read the tutorials, we need to read documentation to make sure that we know what we're doing, kind of. But that was pretty much it. I did not want to get into how mesh simplification, mesh reduction, or mesh remeshing actually works. That's a whole other beast. Okay, then people smarter than me, like Ryan Schmidt, could probably talk much better about that. So beautiful. So that was it for today. I hope this was fun, and I hope you found this interesting. And now my invitation to you is to go out there and check out in the wild what libraries for C# are available out there that you think could be interesting to wrap up into your own plugins, your own components, bring into Grasshopper, use them, etc., etc. Always remember that people who are putting effort in making open source contributions are humans. So credit, if they require it, is a very good thing to give them. Even if they ask you to not use their code for commercial purposes and license it, that's please also use fair practices for that. All those things are very important to keep in mind. Okay. And with that, this video is done. Thank you very much for being here. If you thought the video was useful, maybe consider subscribing to the channel, maybe liking the video, maybe turning on notifications, all those modern YouTube things that we do these days. Thank you very much and see you on the next video. Bye bye.